Some people are fast learners. Some learners are a little slower. And then there are some learners that are so slow it makes you want to kill yourself. And then there's me. Holy heck, dude. This is the 4th video on Quaternions. And I feel like I'm just like scraping the bottom. Like I'm getting the last leftovers, the crumbs of the table on what I'm trying to, like what I can learn from these videos. So anyway, today we're not stopping the video until I understand what Quaternions are to a sense that I feel like I've accomplished something. So I got a couple videos lined up. I've been doing research on my own. Which is actually pretty cool. I did some work, so hopefully like we can go over that. But this is it. This is all or nothing. We're going to go in. Going to go over is called Visualizing Quaternions, 40 numbers with a stereographic projection by 3 blue, 1 brown. This is like one of the top videos that come up when you search. And I think like, I don't know, like I saw this video a bunch of times, but I wasn't like, I don't know, maybe his other video was really confusing, so I didn't bother to look at it all. But I watched through this once already, and it was great. I think going through it one more time as a refresher will be incredible. And yeah, let's just jump right into this.
Certain representation of a specific motion happening on a 4-dimensional sphere being represented in our 3-dimensional space.
Okay, even right off the bat, look at this animation that he just did here. Like, holy heck. Like, watching the sphere as it grows, like in 4-dimensional space, rotate, right? This is all about rotation. Holy heck, dude. And so, yeah, like watching this 4-dimensional sphere as it translates or rotates, it's like rotating this inner circle thing. I think that's just so helpful for visualization. Like, holy heck, really good. Great. Let's turn on the
specific motion happening on a
sound.
4-dimensional sphere being represented in our 3-dimensional space, one which you'll understand by the end of this video.
3 blue, 1 brown.
Are an absolutely fascinating and often underappreciated number system from math.
Do I know all these numbers? I know the real numbers. That's a real number right there. No complex numbers. Quaternions, that would suck. I feel like if I didn't know what I still don't know what those are. Rationals, got that. P-adic numbers. I actually don't know what that is. I don't. And octonions, that I'm not touching that. But let's work the P-adic. That's not. P-adic numbers. What are those? Let's go to Wikipedia. P-adic numbers. Number theory. Given a prime number, P-adic numbers form an extension of the rational numbers, which is distinct from the real numbers. Though with some similar properties, p-adic numbers can be written in forms similar to infinite decimals. For example, comparing the expansion of the rational number 1/5 in base 3 versus the 3-adic expansion. Okay, base 3 means, yep, we're going in base 3s. I don't know why I said that twice, but then 3-adic, 1, 2, 1, 0, 1, 2, 1, 0, 2. Okay, this is for another video. We're not fetch. All right, I don't know what those are still.
Complex numbers are a 2-dimensional extension of the real numbers. Quaternions are a 4-dimensional extension of complex numbers. But they're not just playful mathematical shenanigans. They have a surprisingly pragmatic utility for describing rotation in 3 dimensions, and even for quantum mechanics. The story of their discovery is also quite famous in math. The Irish mathematician William Rowan Hamilton.
Dude, the amount of times I've heard of this guy is insane now. Like, Hamilton is just like as core of a memory to me now as my parents. Like, I would know Hamilton like on the back of my hand. Or I sleep and I say his name because I've been just.
His son would ask him every morning whether or not he had figured out how to divide triples, and he would always say, "No, not yet." But
okay, no, that's not true. No, he did not come. Well, Papa, can you multiply the triplets yet? No, he didn't. You liar. That's not true.
1843, while crossing.
It is true. I just don't want to believe that some kid probably knew more about this than I did.
The Broom Bridge in Dublin, he realized with a supposed flash of insight that what he needed was not to add a single dimension to the complex numbers, but to add 2 more imaginary dimensions.
2 more dimensions!
Imaginary dimensions describing space, and the real numbers sitting perpendicular to that in some kind of 4th dimension. He carved the crucial equation describing these 3 imaginary units into the bridge, which today bears a plaque in his honor showing that equation. Now, you have to understand, our modern notion of vectors with their dot product and the cross product and things like that didn't really exist in Hamilton's time, at least not in a standardized form. So after his discovery, he pushed hard for Quaternions to be the primary language with which we teach students to describe 3-dimensional space, even forming an official Quaternion society to proselytize his discovery.
Wow, look at that. Look at that group of fine-looking gents. Dang, they're cool. Yeah, we're part of the Quaternion society. You want to go out later?
Now, unfortunately, this was balanced with mathematicians on the other side of the fence, who believed...
Sorry, let me full screen this, actually. I just realized I'm not full screening. Let's go back.
Now,
My bad.
unfortunately, this was balanced with mathematicians on the other side of the fence, who believed that the confusing notion of quaternion multiplication was not necessary for describing 3 dimensions, resulting in some truly hilarious old-timey trash talk legitimately calling them evil. It's even...
Do you guys think that like Quaternions were like the new hype thing in the 1800s that people were just like, no, it's evil. Don't go. It's like kind of like TikTok, like low key, like Quaternions was like the TikTok of the 1800s. Like they're like these kids doing the Quaternion stuff. It's bad for your brains. And I don't know. I thought that was kind of funny. Do you think they have? Oh, sorry. Do you think they have like a Quaternion TikTok dance? If not, if one of you nerds out there, please make me a Quaternion TikTok dance and I'll review it because that would be so lit. It'd probably like go something like, okay, thumbnail.
It's even believed that the Mad Hatter scene from Alice in Wonderland, whose author you may know was an Oxford mathematician, was written...
Dude, I've never seen Alice in Wonderland. Like I don't think I've actually seen that whole movie through. Like I know bits and pieces, but it kind of freaked me out as a kid, low key.
in reference to quaternions, that the chaotic table placement changes were mocking their multiplication, and that certain quotes were referencing their non-commutative nature. Fast forward about a century, and the computing industry gave quaternions a resurgence among programmers who work with graphics and robotics and anything involving orientation in 3D space. And this is because they give an elegant way to describe and to compute 3D rotations, which is computationally more efficient than other methods, and which also avoids a lot of the numerical errors that arise in these other methods. The 20th century also brought quaternions some more love from a completely different direction, quantum mechanics. You see, the special actions that quaternions describe in 4 dimensions are actually quite relevant to the way that 2-state systems, like spin of an electron or the polarization of a photon, are described mathematically. What I'll show you here is a way to visualize quaternions in their full 4-dimensional glory. It would surprise me if this approach was fully original, but I can say that it's certainly not the standard way to teach quaternions, and that the specific 4-dimensional right-hand rule image that I'd like to build up to is something that I haven't really seen elsewhere. Building up an understanding for this visual will take us meaningful time, but once you have it, there is a very natural and satisfying intuition for how to think about quaternion multiplication. It won't be until the next video that I show you how exactly quaternions describe orientation in 3 dimensions, which is for some people the whole reason we care about it. But once we're able to go at it armed with the image of what they're doing to a 4D hypersphere, there's a pleasing understanding to be had for the otherwise opaque formulas characterizing this relationship. The structure here will be to start by imagining teaching complex...
Ew! Oh, who is this guy? That doesn't look like anything. Don't look into it.
To someone who only understands 1 dimension, then describing 3D rotations to someone who only understands 2 dimensions, and ultimately to represent what quaternions are doing up in 4 dimensions within the constraints of our 3D space.
Linus the Line
Our first
Lander.
character is Linus
Oh,
the Line
again,
Lander,
please
whose
stop.
mind
It's
only grasp the 1-dimensional geometry of lines and the algebra of real numbers. We're going to try to describe complex numbers to Linus, and it's really important for you to empathize with him as much as you can during this, because in a few minutes, you're going to be in his shoes. On the one hand, you could define complex numbers purely algebraically. You say each one is expressed as some real number plus some other real number times I, where I is a newly invented constant whose defining property is that I times I equals -1. Then you say to Linus, to multiply 2 complex numbers, you just use the distributive property, what many people learn in school as FOIL. And you apply this rule that I times I equals -1 to simplify things down further. And that's fine, that totally works, and the standard textbook way to introduce quaternions is analogous to this, showing the algebraic rules and calling it done.
okay.
But I think
I can dig
something
this.
is missing if we don't at least try to show Linus the geometry of complex numbers and what complex multiplication looks like, since the problems in math and physics where complex numbers are shockingly useful often leverage this spatial intuition. You and I, who understand 2 dimensions, might think of it like this. Think of Z as a sort of function acting on W, rotating and stretching it in some way. I like to think of this by broadening the view and asking, what does Z do to the entire plane? And you can think of that bird's eye view action by imagining using one hand to fix the number 0 in place, and using another hand to drag the point at 1 up to Z, since anything times 0 is 0, and anything times 1 is itself. And in 2 dimensions, there is one and only one stretching rotating action on the plane that'll do this. This is also how I'll have you thinking about quaternion multiplication later on, where the number
So essentially, like, he just took, you can imagine here, he took whatever this triangle is, and he just mapped it to this big triangle. So it's like this edge is this edge right here. That's kind of cool. I
on
just
the
noticed that
left
pattern.
acts as a kind of function to the one on the right. And we'll understand this function by seeing how it acts by transforming
Oh, I know
space.
this. I know this
Although
diagram way
instead of
too well.
rotating 2D space,
Oh,
it is
yes.
a sort of double rotation in 4D
Do your
space.
thing, dude.
By the way, if you want to review thinking about complex numbers as a kind of action, a good warm-up for this video might be the one I did on e to the pi I, explained with introductory group theory. Now, Linus the Linelander is pretty comfortable with the idea of stretching.
Oh, he's comfortable.
Multiplication by real numbers.
He's comfortable, all right.
Maybe it's a little weird for him to think about stretching in multiple dimensions, but it's not fundamentally different.
You know what else stretches? Just
The
kidding.
difficult thing to communicate to Linus is rotation. Specifically, focus on the unit circle of the complex plane, all the numbers a distance 1 from 0, since multiplication by these numbers corresponds to pure rotation. How would you explain to Linus the look and the feel of multiplying by these numbers? At first, that might seem impossible. I mean, rotation is just such an intrinsically two-dimensional idea. But, on the other hand, rotation involves only one degree of freedom. A single number, the angle, specifies a given rotation uniquely. So, in principle, it should be possible to associate the set of all rotations to the one-dimensional continuum that is Linus's world. And there are many ways you could do this, but the one I'm going to show you is what's called a stereographic projection.
Holy, how am I supposed to read that? Oh,
It's a special way to map a circle onto a line, or a sphere into a plane, or even a 4D hypersphere into 3D space.
holy. This is like a fever dream I've had before, I swear.
For every point on the unit circle, draw a line from -1 through that point, and wherever it intersects the vertical line through the circle's center, that's where the point of the circle gets projected. So, for example, the point at 1 gets projected into the center of the line. The point I actually stays fixed in place, as does -I. All of the points on that 90-degree arc between 1 and I will get projected somewhere in the interval between where 1 landed and where I landed. As you continue farther around the circle on the arc between I and -1, the projected points end up farther and farther away at an increasing rate. Similarly, if you come around the other way towards -1, the projected points end up farther and farther on the other end of the line.
That makes
This
sense.
line of projected points is what we show to Linus, labeling a few key points, like 1 and I and -1 all for reference. Technically, the point at -1 has no projection under this map, since the tangent line to the circle at that point never crosses the vertical line. But what we say is that -1 ends up at the point at infinity. This is a special point you imagine adding to the line, where you would approach it if you walk infinitely far along the line in either direction. Now, it's important to remember, and to remind Linus, that what he's seeing is only the complex numbers that are a distance 1 from the origin.
Linus, you're only seeing the complex numbers that are 1 from the origin. Just want to let you know.
Linus doesn't see most numbers, like 0 or 1 plus I or -2 minus I, but that's okay, because right now we just want to describe complex number z, where multiplying by z has the effect of a pure rotation, so he only needs to understand the unit circle. For example, when we take the number I and multiply it by any other complex number w, the effect is to rotate by 90 degrees counterclockwise.
Let's watch it again.
Complex number w.
So if you multiply I by the complex number W, which is the complex number W in this case? Wait, pausa.
For example, when we take the number I and multiply it by any other complex number w,
Oh, any other
the effect
complex
is
number.
to rotate by 90 degrees counterclockwise.
And this is because, I don't know.
And when we
That's a good
apply
question.
this action to the circle being projected down to the line for Linus, what does he see? Well, it's a bit of a strange morphing action on the line, one which I want you to become familiar with for something we'll see later on. It's easiest to understand by following a few key reference points. I times 1 is I, so that means the number 1 should move up to I. I times I is -1, so the point at I slides off to infinity. I times -1 is equal to -I, so that point at infinity kind of comes back around from the bottom to the position 1 unit below the center. and I times negative I is 1, so that point at negative I slides up to 1. Even though this is kind of a weird motion, it lets us communicate some important...
Does that make sense, right? You start at 1 times I brings you up to I. I see what's going on. Okay, I'm picking it up.
Slides up to 1. Even though this is...
So sorry to explain. So 1 times I brings you up to here. I times I brings you up to negative 1. And because I is kind of like this y-axis or like the imaginary axis here, it's that's interesting. That's interesting. And because if you were to multiply by any other complex number, so let's say like this is root 2 over 2i. If this is 45, this is root 2 over 2i, root 2 over 2. Multiply by that gives you a complex number, which would make you end up on this line. Okay.
This is kind of a
all right.
motion.
Yeah, I get this. I get this.
Some important ideas to Linus. For example, multiplying by I 4 times, which corresponds to rotating by 90 degrees 4 times in a row, gets us back to where we started. I to the 4th equals 1. Here, to get more of a feel for things, let me just show the circle rotated at various different angles. On both the left and the right half of the screen here, I'm putting a hand on the point that started at the number 1 to help us and to help Linus keep track of the overall motion.
That's kind of cool. Okay. Oh, thank goodness we're done with Linus. That
Next,
noodle-looking
let's
dude.
introduce Felix the Flatlander, who only understands two-dimensional
Okay, that was really creative of them
geometry.
reusing assets.
Imagine trying
Okay,
to
I'll
explain
be with it. It's okay.
rotations of a sphere
I wouldn't do
to
anything better.
Felix. In the spirit of transitioning from complex numbers to quaternions, let's extend the complex numbers with its horizontal axis of real numbers and its vertical axis of imaginary numbers with a third axis, defined by some newly invented constant, j, sitting 1 unit away from 0,
Oh my gosh.
perpendicular to the complex plane.
It's a J.
Instead of having this new axis in the z direction, like you might expect, for a better analogy with how we'll visualize quaternions, we'll want to orient things so that the I and the j axes sit in the x and the y directions, with the real number line aligned along the z direction. So every point in 3D space is described as some real number plus some real number times I plus some real number times j. As it happens, it's not possible to define a notion of multiplication for a 3D number system like this that would satisfy the usual algebraic properties that make multiplication a useful construct. Perhaps
Multiplication
I'll
isn't
outline why
useful.
This is the case in a follow-on video, but staying focused on our current goal, think about describing 3D rotations in this coordinate system to Felix the Flatlander. The unit sphere consists of all those numbers which are a distance 1 from 0 at the origin, meaning the sum of the squares of their coordinates is 1. We can't show all of 3D space to Felix, but what we can do is project this 2D surface to him and give him a feel for what reorientations of the sphere look like under that projection. Analogous to what we did before, stereographic projection will associate almost every point on the unit sphere with a unique point on the horizontal plane defined by the I and the j axes. For each point on the sphere, draw a line from -1 at the south pole through that point and see where it intersects the plane. So the point 1 at the North Pole ends up at the center of the plane. All of the points of the Northern Hemisphere get mapped somewhere inside the unit circle of the IJ plane. And that unit circle, which passes through IJ, I, and -j, actually stays fixed in place. And that's an important point to make note of. Even though most points and lines and patches that Felix the Flatlander sees are going to be warped projections of the real sphere, this unit circle
What's funny about this part is they're definitely using Quaternions to do those different angles, like that overhead angle. It's kind of like meta. It's like extra meta in the angles.
Sees are going to be warped projections of the real sphere. This unit circle is the one thing that he has, which is an honest part of our unit.
So it's the one thing I only have right now, dude. I'm struggling.
Projection. All of the points in the southern hemisphere get projected outside that unit circle, each getting farther and farther away as you approach -1 at the South Pole.
It's like the Mickey Mouse Clubhouse.
-1 has no projection under this mapping, but what we say is that it ends up at some point at infinity.
That makes sense.
That point at infinity is
it's kind of like that line.
No matter which direction you walk,
goes off infinitely.
As you go infinitely far out, you'll be approaching that point. It's analogous to how if you walk any direction away from the North Pole, you're approaching the South Pole. Now let me just pull up a view of what Felix sees in 2 dimensions. As I rotate the sphere in various ways, the lines of latitude and longitude drawn on that sphere get projected into various circles and lines in Felix's space. And the way I've done things up here, the checkerboard pattern on the surface of the sphere is accurately reflected in the projected view that you see with Felix. And the pink dot represents where the point that started at the North Pole ends up after the rotation. And that yellow circle represents where the equator ended up after the projection.
Yep.
The more you put yourself in Felix's shoes right now, the easier Quaternions will be in a moment. And as with Linus, it helps to focus on a few key reference objects rather than trying to see the whole sphere. This circle, passing through 1, I, -1, and -I, gets mapped onto a line which Felix sees as the horizontal axis. It's important to remind Felix that what he sees is not the same thing as the I-axis. Remember, we're only projecting the numbers that have a distance 1 from the origin, so most points on the actual I-axis, like 0 and 2i and 3i, etc., are completely invisible to Felix. Similarly, the circle that passes through 1, j, -1, and -j gets projected onto what he sees as a vertical line. And in general, any line that Felix sees comes from some circle on the sphere that passes through -1.
This is because, right, because the lines are coming from -1 out, and they're pushing out, and they're intersecting the middle plane. So what he's seeing is not the 0, right? He's seeing 1, and then whatever this I value is, or not I, whatever this value is on the I-axis. So it's like pushing out, going out, intersecting this plane, and then the value is whatever's here, right? It's a map. Okay.
In some sense, a line is just a circle that passes through the point at infinity.
Sure, yeah, that makes sense.
Now think about what Felix sees as we rotate the sphere. A 90-degree rotation about the j-axis brings 1 to I to -1, -1 to -I, and -I to 1. So what Felix the Flatlander...
Yeah, so like looking at that, right? Let's like focus on this red circle. This red circle is vertical, so he sees a line, right? But as this line is going to curve, it's going to start to show its like curvature, right? So I'm using my hands. I can't see my hands. I was using the mouse. So as it starts to curve, let's watch this line. So this is like the vertical view of the red line.
1 to I to
and then as it starts to curve, you start to see its arc. And because the lines are going from the bottom, right, they're projecting this really big circle because these lines out here can... Wait, where's the -1?
90-degree rotation.
Yeah, so start right here, right? As it turns...
brings 1 to I to -1.
Right? Because then these lines protruding out. I understand how this works. Hopefully you do too. I'm not going to try to explain it, even though I said I would. Hopefully that makes sense.
The Flatlander sees is an extension of the rotation that Linus the Linelander was seeing. Notice also that this action rotates the IJ unit circle to the position where the 1J unit circle used to be. So what Felix sees is his yellow unit circle getting transformed into a vertical line, while that red vertical line gets transformed into the unit circle. Of course, from our perspective, we know this is all just rigid motion. No actual stretching or morphing is taking place. All of that is just an artifact of the projection. Similarly, a rotation about the I-axis involves moving 1 to j, j to -1, -1 to -j, and -j to 1.
I wish they showed some like soft lines of where they're coming out for the projection. I think it might be helpful.
This rotation turns the IJ unit circle into the 1I unit circle, which to Felix looks like the unit circle getting transformed into a horizontal line.
I dig this.
Rotation about
my homeboy in the corner is just like, what the fetch is he still doing? He doesn't get any of this, like me.
Since the whole projection simply gets rotated about the origin, where the only points staying fixed in place are 1 at the origin and -1 off at infinity.
That's cool. Okay. Oh, yeah. You, the 3D lander.
The complex numbers included the
this
real
is you
numbers
guys.
with a single extra quote-unquote imaginary dimension, represented by the unit I, and that the not actually a number system thing we had in 3 dimensions included a second imaginary direction, j, the Quaternions include the real numbers together with 3 separate imaginary dimensions, represented by the units I, j, and k. Each of these 3 imaginary dimensions is perpendicular to the real number line, and they're all perpendicular to each other somehow. So in the same way that complex numbers are represented as a pair of real numbers, each quaternion can be written using 4 real numbers, and it lives in 4-dimensional space. You often think of this as being broken up into a real or scalar part, and then a 3D imaginary part. And Hamilton used a special word for quaternions that had no real part and just ijk components, a word which was previously somewhat foreign in the lingo of math and physics: vector. On the one hand, you could just define quaternion multiplication by giving the rules for how I, j, and k multiply together, and saying that everything must distribute nicely. This is analogous to defining complex multiplication by saying
So this is just one thing I wanted to quickly go over, because this is a question I had for the last one. I didn't really get what was going on here, but I wrote it down. Let me take a picture real quick. Okay, hopefully I can go over this. I'm going to airdrop this and show it on the screen. Okay, so here's my work, right? So I just rewrote, I rewrote this guy, I rewrote it down, and I just foiled it out because I didn't really understand what it was saying, and I didn't understand why these were negative and like why only these last ones were negative and why these had the I's. I just did W1 times W2, just distributed it, and then each line is the next variable being distributed. And then you get this guy right here. So then what I first did is I remembered, okay, I times I or j times j, k times k, right? Or from our equalities here equal -1, right? So these equal -1, so I took out the I, j's, and k's, and then I rewrote them here. So that's our first part right here. And then if you look through all the rules, you'll see, like, for instance, this first one right here, x1i, y2j is, right, x1, y2, I times j is equal to k. So you can just rewrite it ij times k, and then that gets thrown over here as, where'd you get put? Oh, yeah. So, yeah, x1, y2, k, because I, j is equal to k, and I put in the third row because it's k. So if you end up distributing through all of them, right, getting through all the numbers, then you do eventually get this equality, because then you could just take out the j's, the k's, and i's outside, and then these last ones are negative because those are the 3 negative numbers in here. I know that I explained that too much, but I just wanted to kind of share how I figured that out, because, yeah, I was a little confused on that last time.
I times I is -1, and then distributing and simplifying products. And indeed, this is how you would tell a computer to perform quaternion multiplication, and the relative compactness of this operation compared to, say, matrix multiplication is what's made quaternions so useful for graphics programming and many other things. There's also a rather elegant form of this multiplication rule written in terms of the dot product and the cross product, and in some sense, quaternion multiplication...
And this part too was also confusing, but I'm assuming, right, it's just another way to write what we did before, like in this example. I think it's just a more elegant way to describe what that's equal to, instead of having to do like this huge foil, right, to distribute. You can just use this instead. I think that's what it's saying. So it's not anything different,
at least
from what I assume. I might be wrong. Who knows?
But just as a deeper understanding for complex multiplication comes from understanding its geometry, that multiplying by a complex number involves a combination of scaling and rotating, you and I are here for the 4-dimensional geometry of quaternion multiplication. And just as the magnitude of a complex number, its distance from 0, is the square root of the sum of the squares of its component, that same operation gives you the magnitude of a quaternion.
Yep, we talked about this.
And multiplying one quaternion, Q1, by another, Q2, has the effect of scaling Q2 by the magnitude of Q1, followed by a very special type of rotation in 4 dimensions. And those special 4D rotations, the heart of what we need to understand, correspond to the hypersphere of quaternions, a distance 1 from the origin, both in the sense that the quaternions whose multiplying action is a pure rotation live on that hypersphere, and in the sense that we can understand this weird 4D action just by following points on the hypersphere, rather than trying to look at all of the points in the inconceivable stretches of 4-dimensional space. Analogous to what we did for Linus and Felix, we stereographically project this hypersphere into 3D space. This label in the upper right is going to show a given unit quaternion, and this little pink dot, will show where that particular quaternion gets projected in our 3D space. Just as before, we're projecting from the number -1, which sits on the real number line that is somehow perpendicular to all of our 3D space and beyond our perception. Just as before, the number 1 ends up projected straight into the center of our space. And in the same way that I and -I were fixed in place for Linus, and that the ij unit circle was fixed in place for Felix, we get a whole sphere passing through ij and k on that unit hypersphere, which stays in place under the projection. So what we see is a...
Okay, yeah. So this real part 1, you know how in that other example, I guess maybe right here is a good example, right? Like the line being stretched goes over the sphere and it's equal to 1. So that's why, like in this example, the inside of the circle is 1 because it's representing the surface of the hypersphere on which we're on point 1 from the origin, but we just can't see that, or it doesn't, like, you know what I'm trying to say? You totally do. I'm just gonna shut up now.
The unit quaternions with positive real parts between 0 and 1 end up somewhere inside this unit sphere, closer to the number 1 in our 3D space, which should feel analogous to how the northern hemisphere got mapped inside the unit circle for Felix. On the other hand, all the unit quaternions with negative real part end up somewhere outside that unit sphere.
That makes sense. Because as you get on the outside of this, or outside of our sphere, you're approaching the tangent line of the bottom of the hypersphere. So you're getting closer and closer to -1, but you'll never actually approach it, or you'll never actually reach it because it goes off to infinity.
The number -1 is sitting off at the point at infinity, which you can easily find by walking in any direction. Keep in mind, even though we see the projection of some of these quaternions as being closer or farther from the origin of our 3D space, everything you're looking at represents a unit quaternion.
That's crazy to think about.
So everything you're looking at really has the same magnitude, the same distance from the number 0. And that number 0 itself is nowhere to be found in this picture. Like all other non-unit quaternions.
I guess this is useful too, because like if you're doing rotation, transformation, I don't know. It seems like this being 1 is very important. I'm just going to say that.
It's invisible to us. In the same way that for Felix, the circle passing through 1, I, -1, and -I got projected into a line through the origin. When we see this line through the origin passing through I and -I, we should understand that it really represents a circle. Likewise, up on the hypersphere, invisible to us, there is a unit sphere passing through 1, I, j, -1, -I, and -j. And that whole sphere gets projected into the plane that we see passing through 1, I, -I, j, -j, and -1 off at infinity, what you and I might call the xy plane. In general, any plane that you see here really represents the projection of a sphere somewhere up on the hypersphere which passes through the number -1.
This is really analogous to earlier, right? This guy, this animation. Yeah, this is like a circle, or yeah, it's a circle projected on the sphere that's represented by a line, right? This line represents this circle, right? On the normal sphere. So in this case, right, where were we? This plane, right, similar to how this sorry, I'm trying to go back to the right spot. Okay, I can't find it. Similar to how this line represents this circle, this plane represents a sphere on the hypersphere, just like he said.
And -1 off at infinity, what you and I might call the xy plane. In general, any plane that you see here really represents the projection of a sphere somewhere up on the hypersphere which passes through the number -1. Now the action of taking a unit quaternion and multiplying it by any other quaternion from the left can be thought of in terms of 2 separate 2D rotations happening perpendicular to and in sync with each other in a way that could only ever be possible in 4 dimensions.
Okay, think of this as a point as or think of P as a point and think of Q as an action. They're both quaternions though, so.
And in sync with each other in a way that could only ever be possible in 4 dimensions. As a first example, let's look at multiplication by I. We already know what this does to the circle that passes through 1 and I, which we see as a line. 1 goes to I goes to -1 off at infinity, -1 comes back around to -I, and -I goes to 1. Remember, just like what Linus saw, all of this is the stereographic projection of a 90-degree rotation. Now look at the circle passing through J and K, which is in a sense perpendicular to the circle passing through 1 and I. Now it might feel weird to talk about two circles being perpendicular to each other, especially when they have the same center, the same radius, and they don't touch each other at all, but nothing could be more natural in 4 dimensions. You can think of the action of I on this perpendicular circle as obeying a certain right-hand rule. If you'll excuse the intrusion of my ghostly green screen hand into our otherwise pristine platonic mathematical stage, you let that thumb of your right
What? Those were just a jumble of words. I'm gonna just
hand
move on.
point from the number 1
fine.
to I, and you curl your fingers. The JK circle will rotate in the direction of that curl. How much? Well, by the same amount as the 1I circle rotates, which is 90 degrees in this case. This is what I meant by two rotations perpendicular to and in sync with each other. Negative J goes to negative K, and negative K goes to J. This gives us a little table for what the number I does to the other quaternions. But I want this not to be something that you memorize, but something that you could close your eyes and you could really see. Computationally,
Yeah,
if
no,
you
I
know
can't.
what a
When I
quaternion-
close my eyes, I just get scared. Like I'm like literal fear goes into my eyes or my soul as I do that. So wait, okay. So I times 1 is I times I is -1, I times J is K, I times K is negative J. I times 1 is I. That makes sense. I times I is -1. No, I don't understand why this is helpful.
that you could close your eyes and you could really see. Computationally, if you know what a quaternion does to the numbers 1, I, J, and K, you know what it does to any arbitrary quaternion, since multiplication distributes nicely. In the language of linear algebra, 1, I, J, and K form a basis of our 4-dimensional space, so knowing what our transformation does to them gives us the full information about what it does to all of space. Geometrically, a 4-dimensional creature would be able to look at those two perpendicular rotations that I just described and understand that they lock you into one and only one rigid motion for the hypersphere. We might lack the intuitions of such a hypothetical creature, but we can maybe try to get close. Here's what the action of repeatedly multiplying by I looks like on our stereographic projection of the IJK sphere. It gets rotated into what we see as a plane, then gets rotated further back to where it used to be, though the orientation is all reversed now.
I think like this is very similar to the that other thing that he showed this guy. Like when we multiply by I, right?
Brings 1 to I to -1, -1 to negative I.
Like this circle is becoming
And negative
flat,
I to
really
1.
similar to how this hypersphere is making, like this flat surface is really analogous to kind of the flatness of the lines when they go around. Yeah, and this visual, like I said, is really helpful to imagining like how
Here's what the action of
changing the
repeatedly
eye,
multiplying
like
by
turning
I
this
looks
4D
like on our
hypersphere
stereographic projection of the IJK sphere.
affects this angle
gets
because
rotated
essentially it's
into
just
what we
turning
see
it
as a
90
plane,
degrees
and
every
gets
time.
rotated further back to where it used to be, though the
And this is the
orientation all
point
reversed
on the
now.
hypersphere. It's on -1. It's on
Then
the
it gets
bottom.
rotated again into what we
Gets
see as a
rotated
plane.
again on the
And after
other
the fourth
side,
iteration, it ends up right back where it
and
started.
then it's back. Yeah. So
As
this
another
this
example,
thing
think
here
of a
is really helpful.
quaternion like Q equals -√2/2 plus √2/2 times I, which, if we pull up a picture of a complex plane, is a 135-degree rotation away from 1 in the direction of I. Under our projection, we see this along the line from 1 to I, somewhere outside the unit sphere. If that sounds weird, just remember how Linus would have seen this same number. The action of
So I'm realizing. So this is I, J, and K, and this real number says part must represent the 4D axis here that we just can't see. Okay, that makes sense.
multiplying this Q by all other quaternions will look to us like dragging the point at 1 all the way to this projected version of Q, while the JK circle gets rotated 135 degrees, according to our right-hand rule.
So at first, when I was doing my research, I kind of got excited because I thought I had a breakthrough, where essentially I'm like, oh, this vector part describes, the stab. You remember the stab again? So you stab in, like, for instance, if the vector was 0.7100, right? And the I would be like 0.71 and then 0 up, 0 this way. So it looked like this. And then the length described the 0.71, described the length. at which, like this animation, as you pull this length out, it's going to be spinning, rotating a certain amount. Okay, I realize this is not the case because the 0.71 isn't necessarily the length here, right? Because it's the negative 0.0 or negative 0.71 and the I component. I'm just going to continue.
Multiplication by any other quaternion is completely similar. For example, let's see what it looks like.
Like, okay, I'm just trying to figure out, like, what is this number? Because I think this is the 4D number. But why is this important? Because I feel like you could describe this point right here with just the 0.71i, right? Because this is just on the I-axis. But I know this, I think that's the hurdle right now.
Like for J to act on other quaternions by multiplication from the left. The circle through 1 in J, which we see projected as a line through the origin, gets rotated 90 degrees, dragging 1 up to J. So J times 1 is 1, and J times J is negative 1. The circle perpendicular to that one, passing...
Let me look back here. Let's go look at the real part of this 3D sphere and see what's happening. So does he have the number? Maybe it's because he doesn't have the numbers. That's probably why it's not as intuitive as I was hoping to. Because this does seem pretty specific to Quaternions. This 0 here is describing, I know this 1, negative 1. I get that's the top and the bottom of the hypersphere. But 0, I guess I'm just trying to figure out what that means. Let's figure out what that means.
And that yellow
So maybe look at this example again. J is 1, and as it rotates,
sees as we rotate the sphere. A 90-degree rotation about the J-axis brings 1 to I to negative 1 to negative I, and negative I to 1.
So J turned from 1 to I, and I to negative 1. But in this case, it goes from 1
and you could really see
to 0. Oh, why did I do that? 0, maybe it's because it's the real part in the 4D axis. Maybe it's the part that we can see. Because, the real numbers are the one protruding out the 3D space. The real numbers are the ones that 2D flat Stanley over here can't see. And these are the parts we can see. So obviously in 3D space, that makes sense. And essentially, it's 0 because it's 1i and 0 is the real part. So 1 becomes 0 because it's the y-axis. Yeah, this axis right here, the real axis. It becomes 0 because this is 0 and then it becomes negative 1. So, as the line goes out infinitely, this is... no, I'm getting confused. I'm getting confused. This has nothing to do with this 4D number because we can't see this number. This is, if anything, the size of I don't even know what it is. We can't see this. This is the 2i that we can see. And I guess maybe trying to map this to a 3D sense, right? If we were to do here, right, this point on the hypersphere is whatever, let's say 45 degrees. This point on the hypersphere is root 2 over 2 j and root 2 over 2 real, right? Because that's what it is. So in this sense, this number right here is root 2 over 2 I and then root 2 over 2 real. So this is the 45-degree angle on the hypersphere. And now I guess I'm just trying to think, which point do we move, right? I think it doesn't really matter, right? Because if we move I along any point here, it's going to move around this circle. So I and the real numbers are they're all locked. That's what it's trying to say. It's it's all rigid. So this point is, I guess, I don't want to say unique, but it's you can't just have root 2 over 2 I times 3 or whatever number before, under 1. It can't be 0.2 because that would leave the sphere, I think, right? It wouldn't be rigid anymore. There's no rotation. You'd be morphing the 4D hypersphere. So I think I'm just understanding. This makes more sense now. It's just a point. And I think maybe you can do rotation for that because root 2 over 2i is always going to give you root 2 over 2, negative root 2 over 2 real. I think. I
Applying
don't know.
this q by all other quaternions will look to us like dragging the point at 1 all the way to this projected version of q, while the jk circle gets rotated 135 degrees, according to our right-hand rule. Multiplication by any other quaternion is completely similar. For example, let's see what it looks like for j to act on other quaternions by multiplication from the left. The circle through 1 and j, which we see projected as a line through the origin, gets rotated 90 degrees, dragging 1 up to j. So j times 1 is 1, and j times j is negative 1. The circle perpendicular to that one, passing through I and k, gets rotated 90 degrees according to this right-hand rule, where you point your thumb from 1 to j. So j times I is negative k, and j times k is I.
Okay, so it seems like there's a lot of just these math things going on too, because that seems really important with the numbers here. So going back, right, like as we rotated 90
For
degrees
j
by
to act
I,
on other quaternions, we see projected as a line through the origin,
or j,
gets rotated 90 degrees, dragging 1 up to j.
okay, and that makes sense, because j times 1 is equal to j. So what is equal to j here? Like, that's my question. What is equal to j? Is it this real part? Or
So j times
let me listen. I'm
circle
trying to listen.
through 1 and j, which we see projected as a line through the origin, gets rotated 90 degrees, dragging 1 up to j. So j times 1 is 1, and j times j is negative 1.
1 up to j, which is 1 up to j, because the real part's gone and it becomes j instead. Because we have to remember we're on a 4D hypersphere, so we're on the 1 at the top of the hypersphere, and as we multiply by 1, right, or j, yeah, as we move j, because we're moving j is the part we're moving, p is the point 1 on the hypersphere, j times 1 is j, so that's where we end up. And as we move another j, then we go on the bottom of the hypersphere.
The circle perpendicular to that one, passing through I and k, gets rotated 90 degrees according to this right-hand rule, where you point your thumb from 1 to j. So
I times j is
I
equal to
is
negative k because of the
and
equalities that we had
times
before.
k is I.
Yep, j times k is I. So as we multiply j by negative k, that's going to be equal to negative I.
In general, for
And then
any
j
other
times I is
unit
equal to k.
quaternion you see somewhere in space, start by drawing the unit circle passing through 1, q, and negative 1, which we see in our projection as a line through the origin. Then draw the circle perpendicular to that one on what we see as the unit sphere. You rotate the first circle so that 1 ends up where q was, and rotate the perpendicular circle by the same amount.
And that just
according to the
determines how much
right-hand rule.
rotation there is. Guys, you can tell, like, now I'm so locked in. Like, before I'm like, oh, this is super funny, we're making jokes and stuff, but like right now it's not funny. Like, it is, but I'm just like, yeah, I really want to know. I really want to figure this out, because I feel like it's something I really want. So we'll see.
Order of multiplication matters. It's not, as mathematicians would say, commutative.
That makes sense.
For example, I times j is k, which you might think of in terms of I acting on the quaternion j, rotating it up to k. But if you think of j as acting on I, j times I, it rotates I to negative k. In fact, commutativity, this ability to swap the order of multiplication, is a way more special property than a lot of people realize. And most groups of actions on some space don't have it.
You know, it's super funny, like as a joke, but like also kind of seriously, I don't think I could solve this Rubik's Cube. Like, I would find a way to mess it up. Like, one turn, it'd be over. Like, one wrong turn. Anyway.
It's like how in solving a Rubik's Cube, order matters a lot. Or how rotating a cube about the z-axis and then about the x-axis gives a different final state from rotating it about the x-axis, then about the z-axis. And last, as one final but rather important point, So far, I've shown you how to think about quaternions as acting by left multiplication, where when you read an expression like I times j, you think of I as a kind of function morphing all of space, and j is just one of the points that it's acting on. But you can also think of them as a different sort of action, by multiplying from the right, where in this expression, j would be acting on I. In that case, the rule for multiplication is very similar. It's still the case that 1 goes to j and j goes to -1, etc., but instead of applying the right-hand rule to the circle perpendicular to the 1j circle, you would use your left hand. So either way, I times j
Makes
is
sense.
equal to k. But you can either think about this with your right hand curling the number j to the number k as your thumb points from 1 to I, or as your left hand curling I to k as its thumb points from 1 to
Almost
j.
done.
Understanding this left-hand rule for multiplication, it involves a process called conjugation, and I'll make a full follow-on
Okay.
video.
I think this is like the end. So, yeah, I feel like, yeah, dude, I'm getting it, and I understand way more than I did. I still don't, I know I keep saying this. This is bugging me. I need to chat GPT this. We're chatting. I'm so done. Chat GPT. Okay, so let's try, okay, why do we multiply Q, V, Q inverse when talking about quaternions? This is just gonna kill me. Chat, please. The old quaternion sandwich tastes like math, dude. Shut up, bro. Okay, I love it. Okay, you want to rotate a 3D vector V using a quaternion Q. Okay, Q is a quaternion representing a rotation. That makes sense. It's just one of these Johnskis, right? Where's the picture? The dot. Where's the dot? All right, anyway. It's just like one of those dots on the spheres. Like this guy. Yeah. It's like that. Okay, it's like that. That's a quaternion that representing a rotation. This represents some sort of rotation because if we take the quaternion, start from the origin, and then we pull out to this point, that represents a rotation in 3D space. A 3D vector you want to rotate, not a quaternion yet. What a 3D vector I want to rotate? Like, what is a 3D vector I'd like to rotate? Okay. Some unit quaternion.
Q and -1, which we see in our projection.
All right, let's just assume that's some 3D vector we want to rotate. Maybe it's like this vector right here. You convert V into a pure quaternion, which is just adding a 0, right? Because there's no real part, because there's no 4D part in the quaternion. And then this is the inverse. That makes sense. I understand more or less what these are. They're a mathematical object that represents rotations. I kind of picked that up. When you apply Q times V times Q inverse, you are rotating V by Q and then immediately undoing any distortion using Q -1, making sure the vector is rotated but not skewed or stretched. That's what I said in the first video. Why am I so smart? Just kidding. I still... That makes sense, but what kind of distortion? It's just skewed or stretching? Think of it like turning a steering wheel. Q is the active turning. V is your original direction. Q resets the wheel after you apply the motion, so only the car's direction changes, not the wheel itself. Oh, that's a great analogy. Chat, you cooked that one. You cooked. Okay. That kind of makes sense, because I imagine it's like some 4D shenanigans, you know? Like, I don't want to... Because, yeah, like I said, I'm going to go with my original theory. I'm going to go with my original theory of how, like, you know, when you multiply by Q, it stretches it somehow, like it said, and then you multiply by Q inverse to keep the rotation, and then... you divide by 2 because the rotation is doubled. I'm going to stay with that. That's going to be my final understanding for now. Hopefully I can just understand this better later. Okay. Yeah. So I think this is just like something that's in 4D. So it's like hard because I want to try to like visualize it, but maybe that's the hurdle right now. I think I was able to kind of dissect this real part, imaginary part type deal. And what it's doing. And I think being able to take this and like pull it through, because I'm realizing this is not okay. Yeah, so this point doesn't matter, right, in the real number, because this point is in 3D. So I think this point maybe I take back what I said before. You can have any point in space, and then this real part defines how much you are going through the hypersphere space, and then thus how much you're rotating. But then again, that's kind of like my original theory of like this point describes the IJK, and then this describes how much you're rotating it. But I don't think that's the case. I don't know. Maybe that is the case, because I searched this earlier. I said I was super excited. I was like, what did I say? I literally like, I watched the video. What I understand right now is the scalar part defines how much the object rotates, I being 90 degrees. So it's not I. It's not I. It's this real number that just describes how much you're rotating, right? Let's see if I copy this and paste if it will like understand. Is the real part being 90 degrees and the imaginary part defined, holy, what is wrong with me? Defines the line which is being rotated on. Let's see what that says. Apparently I'm really close. Just a couple tweaks. Let's see what's wrong. The imaginary part defines the line axis which is being rotated on. The vector part points the direction of rotating axis, like a skew arrow points. Okay, that's good. The scalar real part defines how much the object is to rotate, the real part being 90 degrees. The scale part W is actually cosine theta over 2. Okay, so it encodes it via a cosine and half the angle. Likewise, the imaginary part is scaled by. So if we wanted, if we wanted to find, like the angle, find the angle of W, we would multiply by cosine inverse and then 2 to get the desired angle. Let's see what that says. Bingo. Boom. Yeah, I just did level up. I leveled up. It's the coolest way to say that. Okay, so it doesn't actually, okay, likewise, X, Y, and Z are the A axis times sine theta over 2. So when theta is 90 degrees, then X, Y, Z is equal to A axis. Okay, so this is getting multiplied by sine 45 degrees. Because I'm assuming it's because it's like a hypersphere, right? Because like you need to multiply by this. Okay, I guess. So in this case, both the scale and the vector parts have the same magnitude, right? 0.707, because the sine and cosine of 45 are equal. Imagine you're trying to describe a spin move in a dance. The x-axis is the line through your spin. Scalar is like the rotation intensity dial, determining how much you've twisted. That's what I thought I was saying, but it's apparently not. What is a... Oh, this is axis. Okay, I've been reading this a-axis or axis, and this is just the axis. Codes what direction you're rotating around. Okay, I think, okay. So what I'm getting at is like the XYZ part is actually like the axis at which defines like it defines a 3D space. 0.5, 0.5, 0.5 is equal to the axis at which it's going times, yeah, okay. We're so close. I feel it. Why is it axis times sine angle over 2? That was not a parentheses. Okay, so why is it like this? Step 1, think of complex numbers first. Remember how complex numbers are used to rotate things in 2D? Yeah, I remember that. Do I remember that though? Cosine theta plus I. Yes, because that's what we were talking about. Oh. Okay, so like, yeah, so like in this example, right? Where's that one with the unit? Yeah, maybe this guy, right? So when we use I for a rotation, when we just want to rotate around this circle, we use something like root 2 over 2 plus root 2 over 2i, right? That's like a 90-degree angle. I might be wrong, but it's a sine. So really, essentially what you're saying is the sine of the angle times or plus I times sine of the angle. That's the rotation part. to get a true rotation. So, okay, so this is just the 3D version of that. And this axis, oh, I just need this. This is the only thing that's killing me. I'm assuming this is direction. Okay, final thoughts. I think I got it. Okay, so this vector part is like the line. It's the direction in which we're rotating. So we can rotate this way, we can rotate this way, we can rotate this way. But this just defines the rotation. The sine theta over 2 describes the angle at which we're rotating. So instead of it being like this vector, it makes it into a, how do I describe this? It's describing a rotation. I'm just going to say this. Adding this makes this describe it as a rotation instead of multiplying it to like another vector in space. So it, I guess, normalizes it. Is that a word? And then this cosine angle over 2 is the amount of rotation we're doing because it's in 4D space. Okay, we got it. We did it. I feel good. I feel so good right now. That's it. Okay. To recap, let's recap. One more time. I guess one more time. This is the direction. Yeah, I feel good about that. This normalizes the direction so we can make it into an angle. This describes how much we're turning that angle. Yes! What was that? Like, it feels like hours. I think I spent like 3 or 4 hours doing this in total, which is like obviously not that much, but for one thing. And maybe like, I feel like a lot of you might be like, yo, you don't actually get it. But hey, I'm feeling good. If I need to understand more about this, after, I'll keep researching because I do want to understand this at a more fundamental level, but I feel like for now, we got it. I think we got it. Now, okay, I do want to make a video teaching this though, because I feel like you don't understand something until you can teach it, and I feel so inadequate in teaching it. So maybe we'll see if that ever appears as a video. But anyway, I'm done. I'm good. See you later.